Last day, I have discussed about the basis function. So before I want to discuss anything about linear algebra, first I want to ask you one question and I will reply that what is noise? We know noise is random in nature. It is completely unpredictable. But why? If why, then another question will come. What is the main, who or what is the main source of this noise? Then on the answer of this question is very, very simple. That most of the reason that may be found in our media, communication media or channel. So when we are getting this answer, channel is responsible for noise. That's why every time we are talking that channel noise. But there may be other noise also that may be found due to our internal circuitry related to the noise known as short noise or thermal noise. Thermal noise mostly related to your heating or effect of the conductor due to random movement of electrons. Same thing when I'm talking about active component instead of passive components, the random movement of electrons that will make some noise, that is short noise. We know these two terms very common for internal noise, that is thermal noise or and short noise. These are common. Instead of that, when I'm talking about the channel, if I know about the channel, then no more circuitry problem. This is simply related to the media, and if it is wired media, then what happens? Some wire attenuation is there. And if I want to tell you a story about digital communication system, then at any time k, I want to send either 1 or 0. It is the basic concept of digital communication because I want to send either binary data in terms of 1 or 0. And when I want to send any one of them, ultimately that may be defined in terms of certain signal, that is our baseband representation. In case of digital communication, I want to tell you one thing. There are two kinds of modulation. One is baseband modulation and another one is band pass modulation. And sometimes this band pass modulation, that is known as passband modulation or band pass modulation, anything you can say. Okay, passband or band pass modulation. So what happened in case of baseband modulation? In case of our baseband modulation, what is the concept behind this? The baseband signal is modified? No, not at all. What is the concept behind baseband modulation? Only the nature is continuous. I told you continuous means for infinitesimally smallest interval of time, if I can define any signal, that is called continuous signal. If it is continuous, that means it is differentiable at every instant of time. That's why it is continuous. But when I can say anything is discrete, what does it mean? That means it is defined for a specific instant of time. And then I will get this kind of data set. And if I can plot it, I will get this output. And instead of t, I need to put it is k. That means k is defined for a discrete intervals. And then I maybe defined some specific sample values like xk. Instead of time function, I want to write xk. That means some specific signal value or sampled value in terms of coded data that may be sent. What happened? In case of baseband modulation, ultimately you need to do three things: sampling, quantization, and encoding. First, you need to collect certain samples. If you can collect the sample, you know about the voltage. If you know about the voltage, you can put into a certain level. What kind of level it is? It is quantization level. If you know that level, if it is quantized level, then another level is there, another level is there. But how to distinguish these points? These are in same level, but how to distinguish them? By putting some code. What kind of code it is? It is encoding. That's why there are three things. One is sampling, then quantization, and last one is encoding. These three things will produce certain discrete signal as digital signal. All the digital signals are not specific, all the discrete signals are not specifically said as digital signal, but all the digital signals, maybe, better to say not maybe, obviously, all the digital signals, obviously, discrete signals. So all the digital signals are discrete signal, but all the discrete signals are not digital. Otherwise, you can do some coding, apply some coding. You can say any discrete signal is digital signal. Same thing, if you can do some other operation, but you can't produce any code, then it is discrete signal, but not digital signal. Simply, digital means you need to put some 1010 bit pattern. Otherwise, it is discrete. Otherwise, it is discrete with respect to this value of k, because it is responsible for its variation in terms of discrete variation. You will get certain specific value of k, xk. You can obtain the specific value of xk. So obviously it is discrete signal. No more confusion about that. But if you can add some 1010 bit pattern over that, you can say it is digital signal, and this is the fundamental concept of our xk. So we have found the continuous signal and this digital signal. When I want to convert continuous nature to digital nature, this is the conversion known as modification. And the baseband signal from continuous nature to digital nature, it is known as the baseband modulation. On the other hand, you know what What is the purpose of carrier? Carrier is required only when I want to send the information over the longest path. If I want to send the information about the longest path, what I need antenna, and antenna height may be reduced using some modulation technique. Modulation here is possible using some carrier who can carry the message. Now, this is related to your passband modulation or band pass modulation. In case of baseband modulation, you know DPCM, PCM, TM, ADM, they are baseband modulation. On the other hand, band pass modulation or passband modulation, they are ASK, PSK, etc. So now, let's talk about the digital signal. We are called the signal XK that may be sent over a wired path. I want to send over a wired path. Basically, baseband modulation, baseband modulated signal that may be transmitted from transmitter to receiver by using wired path or wireless path. But in case of band pass modulation, mostly it is done for wireless communication. So if I am talking about baseband modulation, I want to send over a certain wired path. What happened? I want to show you one thing that one level binary one that may be defined by this thing. This is the ultimate shape. This is 5 plus 5 volt level, and this is 0 volt level. When I want to send this higher level for one transmission, binary one transmission, that time this 0 volt in voltage level may be sent to the information about binary 0. Now, what about the duration? Duration is a bit duration. It is the bit duration. It is the periodic duration, periodic interval. One particular period is there. I can say it is TB. TB is the bit duration. If it is true, then it is also known as bit interval, bit duration or bit interval. And in case of zero transmission, don't make the voltage change over the interval like this. We want to send the signal over a wire at the receiver. We have to collect up all of the energy. When I want to transmit this thing over a certain wired path, this is the transmitter side. And this is the receiving area, then this is the media. This is the media. What happened? This receiver can receive this information after traveling this information over this particular wired path. Now, what happened? The energy, ultimately, this will produce certain energy. This energy may be received at this receiving section. So we have an integrator to accumulate all the energy at the receiving section. So I need one integrator. This is the integrator which can accumulate all the energy in this receiving section. After that, what I need to sample out ultimate information, right? So after that, when this mathematical operation is done, like integrator over the period 0 to t, then one sample may be taken at the time kt. I can say this t equal to kt, that is the sample collecting interval, particular interval. If I can put one sample circuitry like this, one switching circuitry like one sampler, then this may be functioned over a certain interval that I can say t equal to kt. Okay. When I can say k equal to specifically 1, then t equal to capital T. Okay. When k equal to 2 and so on, sending repeated different digital data. Ultimately, what can be received at this particular section? We can receive y equal to, or yk, better to say, at a certain interval, kth interval, I can say yk, that is yk is equal to h into xk. That means h times of xk. Okay, xk is the transmitted signal, this one. Now, h is the amount of attenuation. Don't think it is the simply gain, right? Because if it is the gain, g, then this may be used to increase this value, or if it can take some different action over this signal, that means this amount of information may be traveled, so some attenuation may be taking place over this wire, so this value may be reduced, this voltage level, the energy level of this thing may be reduced due to this component. So don't think the gain, the path gain, this channel gain is always used to enhance the amplitude. It's not true for all the times. Sometimes it is also happened that the word media that may be function like an attenuator. That means it can attenuate some energy from the transmitting signal. That means the energy level may be dropped. When it can be happened, this H is the amount of attenuation. It's not a number that accounts for 5 volt or like that. This attenuation due to the wire or this media and how much accumulated in the integral, that is the most important thing. Before the integrator, how much value can be received, and after this integrator, total value, total energy, total how much energy can be accumulated, that is most important. Then we need to sample it out. Because of this attenuation, so what I need to amplify it. Every time, in case of superposition, super heterodyne receiver, in case of super heterodyne receiver, before the detection, we need RF amplifier. That means the received signal that may be amplified. So amplifier is the part of the receiver, and that is used to enhance the voltage or energy level. Otherwise, some attenuation may be taken place and you will get the very, very feeble signal, which is not our main objective to receive from the transmission section. Okay, so when I want to draw it, then I can draw in this way. First, I can write xk, the transmission for transmitted signal, which is, you can say, input. After that, there are the longest media or smallest media, like this. This is wired media. I want to assume it is wired media. I want to assume it is wired media. So this wired media is here. After that, what I need some amplifier. Why should I need amplifier? Because some attenuation may be taking place due to this wired media. So I want to amplify it by an amplifier. This is the reason behind this. So when I can do this using amplifier, after that, you need one integrator. You need one sampler. And ultimately you will get your output, right? Output may be like YK. So this portion is our original receiver section. Okay, so we have understood the basic block diagram. Now, because of this attenuation, we have applied this amplifier's block diagram. So all of these, I mean to say, accumulation after attenuation are accounted in our age. So this thing and this thing, they may be used a greater part in case of our receiving proper input before integrator. So it turns out in our receiver, the way to build this and make it real by setting an operating voltage for this one, and this one. That means you need one power supply. You need power supply. When you turn on the power supply, the process is associated with some electronic concept. That means electron movement over here, and you will get some heating effect. When the electrons can move in random way, you will get some random motion, and that random motion will create some heating effect. When you get this heating effect, that is responsible for something else. I want to tell you. Now, due to this amplifier, it is also possible to enhance this random movement. Okay, because when it may be hitting up, then electronic movement more, and you will get some output from this side that may be passed towards this in any way, and that is more due to more electron movement in random nature. So one thing, we have found the noise that is entered over this medium, but that is not the main issue of our discussion right now. I have considered that no more noise can be inserted, because this is wired media. Only thing is the problem that is related to attenuation. That's why I have taken the help of amplifier. If it is wireless, obviously noise may be pushed over this medium. Now, one thing we have found yk is equal to hxk in case of our previous discussion. But now, another thing that may be found over here, that random motion of electron will generate some heating effect, and that heating effect will create some additive nature over there h into xk, h into xk. That means the channel gain with this input signal that is associated with some additive effect. I don't know about this additive effect, but the motion is unpredictable in nature. So what I can say, obviously, I can say it is noise. And I do not want to write anything over here because I can't say this shape is directly changed. This shape is absolutely same, but something is added over here, and I will get the complete expression due to this one. With this is additive noise. This is additive noise. So why noise? Because unpredictable in its nature. Due to heating effect, electron can move in any direction. So that's why it is additive. Additive doesn't mean something is added over here. Why added? Because of this thing, the power to up and the heating effect, you will get electron movement, and due to this electronic concept, you will get something is added over here. And this thing is absolutely unpredictable in nature. That's why I can say additive noise, which is totally undesired thing. So that's why I can say noise. It is not the desired signal. So we have found yk is equal to hxk plus nk. But we know sometimes it is known as not additive noise, but also one thing is present for here. That is Gaussian noise. Why Gaussian? Who is responsible for this Gaussian nature? That I want to tell you now. All the electrons can move and their effect is random in nature, that is found over here. The probability density function, if I want to draw it over here, then I can draw in this way. This is something like this, and with respect to some thing I want to draw, I want to write it as some n is the variable, and the distributions, the density function, something like this. This is absolutely like this in nature, and when I will get this out, and when I will get this output, this is absolutely like bell shape in nature, because this shape is known as bell shape. That's why it is it can be said as bell shaped nature. Mathematically, it is bell shaped nature, so I want to mention it as bell shaped nature. What happens when the value of n is bigger, like this, you will get this Pn is very, very small, and when the value of n is very small, you will get bigger value of Pn, and but it is limited within this maximum value. And we know PDF it is probability density function which doesn't cross the limit of 1. I will tell you, I will discuss what is PDF CDF, but before that, from the primary knowledge, I think you know PDF is equal to less than or equal to 1, and it may belong within 0 to 1. Now, after that, it is it can be said absolutely it is equally likely in nature, because in this positive side and this negative side, everything is equally distributed, right? So this is this shape is known as bell-shaped nature, and from the name of scientist Gauss, we can say it is Gaussian shape, because he was developed this particular curve. And now I want to tell you one thing, most important thing. If we measure the YK output, then plot a histogram. If I can draw a histogram, then that histogram will be able to fill the absolute bounded area within this particular shape. That means the histogram that can follow this bell-shaped nature, which is Gaussian in nature, Gaussian curve. So what is this? But this noise is not only additive noise. Better to say we can write additive Gaussian noise. Additive Gaussian noise. Uh, and it is most important, additive Gaussian noise. What is additive Gaussian noise? I have mentioned over here. And another thing I want to tell you, that is, if I can say this noise, then I need to write yk is equal to hxk plus nk, where nk is the additive white Gaussian noise, and its nature is defined by one thing that is known as the distribution IID, and it may follow this IID. What is IID? Identically, independent independent and identically distributed. Independent, identically distributed in nature. Okay, why independent? Why it is independent? Because this value of nk is independent of any value of k. It may be anything due to heating effect. It can say it may be depending upon the particular value of k, the motion of the electron, that is random in nature, so it cannot be predictable for any instant. So anything, it may be increased, it may be decreased for any instant. So it is independent of this k, and identical in nature, because we have found it is identical in nature. So it is independent identically. And what kind of what is this? This is the distribution ultimately, and that's why this is it may follow certain distribution, and that's why it is known as independent and identically distributed noise, IID noise, IID Gaussian additive Gaussian noise, IID additive Gaussian noise. This is the basic concept of the additive Gaussian noise. Okay. Now I want to mention the very important thing, PDF. Already I told you in the previous part, that is white, sorry, not white, additive Gaussian noise. In case of additive Gaussian noise, we have seen one term that is used PDF, and PDF that may be seen as like our bell curve nature. And now I want to mention one thing. Say I have one data set. This is my data set. These are the number of data that may be found for height and corresponding mapping over there for weight. And this is the particular height and corresponding weight that may be found as 90 and something like that, and so on and so forth. There are a large number of data set. When I want to plot over here, I will get with respect to this weight, I'm getting some count, and what happened, I'm getting something like this. What is this particular intervals? Say this is 60, say this is 70, say this is 70. Now after that, this is say 80, say this is 80. Now say this is 90, say this is 100, say this is 110, say this is 120. And in this way we'll get, say, it is this 130, 140, etc. Now when this is the weight, with respect to weight, we are getting some count. This number of values may be found within 60 to 70, and how many values may be found in within 60 to 70, then it is not absolutely count. Count is the most important thing when I want to draw simple histogram. Histogram means this number of value, this number of value may be found with certain weight, that is within 70 to 80, 60 to 70, something like that. When I want to write, say, within 70 to 80, some value may be found, that within 70 to 80, some large data set. From the large data set, we will get, say, 5 values are there or 4 values are there. Then you need to put over here. If you can put it, then you want to count. Actually, you want to count these number of values may be found within this column. That these are the value, this is the value for that may be found within this region. That is the count. But when I want to write something else, I want to find a shape. A shape means I want to draw a smoother region that may be drawn like bell-shaped graphical plot. And that time this is not count. Instead of that, you need to write this is percentage of distribution. So what happened in case of this thing, it may be drawn like this. This is something like this. This is the bell-shaped curve, which is absolutely Gaussian in nature, and you will get with respect to this weight, right? This is the plot, and this is percentage of distribution. This is not count. Right now, this is percentage of distribution. And this is the significant thing right now. That time, if I want to mention this point, and which is found to be at this 70. What is the significance of this point? It means this is the density region from 60 to 70 that is found as this particular region. And if I want to write it as 0.1, what does it mean? I do not want to write any count. I want to write the percentage value. That means 10% of the data set that may be found within 60 to 70. Same thing when I want to write some point at 80 and I want to write it is 70 to 80. This may be found this particular region, and then I want to write it is 0.25. That means 25% of data set that may be found within 70 to 80. And in this way, when I want to write it, then I will get say 50%. That means I want to write say 0.5. That means 50% of data set that may be found within this particular region. And this is the main significant thing. This is 50% means total thing. This 25% means this is the total things. This below this 80. Okay, I want to draw it for certain region from 60 to 80. Here I want to draw it for 60 to 110, something like that, and then I will get these values. When I can add up all those values, then I will get one density. That is our PDF. And you must remember this. This is the overall added or combined thing. When we will combine all these values, all those values like 0.1, 0.25, 0.5, etc., with respect to various weight region, then we will get around 100% value. That means maximum 1. It can't go over that value 1 or 100%. The overall value is restricted between 0 to 1. Minimum value is 0 and maximum value is 1, because this is probability. Probability means it is bounded within 0 to 1. If it is PDF, next day I will tell you what is CDF and what is the relationship between CDF and PDF. And this is everything about PDF. I think I have discussed Gaussian noise and what is the purpose of this term. Specifically, I can say Gaussian. Why I want to say Gaussian? And next to that, I have mentioned what is PDF. And I have shown you this particular plot and how to explain PDF that I have discussed in this lecture. If you need anything else, you can join our meeting right now.